Before we talk about the topic of this video, finding sines and cosines of special angles, I want to point something out that I kind of overlooked in the previous video. And that is that when I spell out the word sine, I spell it as sine, S-I-N-E, and cosine is C-O-S-I-N-E. And those are the official names of these functions, the sine of an angle, the sine of t, or the cosine of theta, right? But when I use them in a formula, I just use the first three letters, sine and cosine. So those are the official abbreviations of those words, except that you never see those abbreviations. And in my opinion, you should never use those abbreviations unless you are using them with an angle name. This is the sine of t or the cosine of theta, for example, right? So be careful only to use sin if you mean the sine of something, or the cosine, cos, the cosine of some angle. It's kind of like saying you would never say log just by itself. It has to be the log of something. Let's say the log of k, the log of a number. You would also never say just the square root. It has to be the square root of something, right? You have to put something in the argument. You have to have something to take the log or the square root of. So you have to have something to take the sine or the cosine of, especially if you're using this abbreviation. These are just the names of the function. So if you're just talking about the cosine function, then you need to write it out. Now, in the previous video, I said that if you knew the coordinates of the point of a point on the unit circle, the example we had was the coordinates, the square root of 3 over 2, comma, 1/2. That you could say, oh, well, in that case, whatever this angle t is, the cosine of angle t is the square root of 3 over 2. And the sine of angle t is 1/2. But how do we know that those are, in fact, the coordinates? And what are the coordinates of the other points around the unit circle? Well, there are several important, quite special angles that we need to know about before we can talk about the sine and the cosine in more general terms. So let's talk about those. When the terminal ray exactly bisects the first quadrant, then the point that we have here is going to have the same x and y coordinate. And the reason for that is that what we have produced here is a right triangle with a 45-degree angle here and a 45-degree angle here. How do I know that? Well, this is a right angle right here. This whole, here, I'll put it in, I'll actually draw it in. This is a right angle, right? This is a 90-degree angle here. And if I cut that angle in half, then what's left, this part right here, this half of it down here, is half of 90 degrees, which is 45 degrees. And since all of the angles in a triangle have to add up to 180, if I don't know what this one is, but I know that one of them is 90 degrees, this one right here is 90 degrees, this one right here is half of this one, you color it that way, this half, that's 45 degrees, right? And if I add those together and then add the angle that I don't know, this one up here, those have to add up to 180 degrees because all triangles, the angles, all three angles in any triangle add up to 180 degrees. Well, this is 135 when I add them together. And when I subtract 135 from both sides, I get that the unknown angle is 45 degrees. Okay, so I mean, you could also say, well, if this one's 90, then these two together have to equal 90. And if this one's 45, this one has to be 45. So there are a couple different ways to go about getting that number. The point is that this is what we call a 45, 45, 90 triangle. Okay, so that's one of our special triangles that we'll be dealing with. And one of the things we know about a 45, 45, 90 triangle, or actually any isosceles triangle where, let me draw it in a different position here, you might recognize this more. Here is an isosceles triangle. You have to believe me here. That these two angles are the same measurement. right? This one happens to be 90. They're not always 90, but that one happens to be 90. But the point is that if these two angles are the same size, then we remember from geometry, I hope, that these two sides are the same length. And so for our triangle up here, this side and this side are the same length. That means that x comma y can be written in this particular case as x comma x because x and y have the same value. Okay? Now, since x and y are equal, we could also write this just as x equals y or y equals x. Then I can write x squared plus y squared equals 1 as x squared plus x squared equals 1 because x and y are the same. Well, now I have common terms, so I can combine them, like terms. So I have 2x squared equals 1. If I divide both sides by 2, I get x squared equals 1/2. And if I want to know what just x is, not x squared, then I'll take the square root of both sides. And that gives me x equals plus or minus 1 over the square root of 2. It's actually the square root of 1 over the square root of 2, which is, square root of 1 is just 1. So in this case, I have x equals 1 over the square root of 2. But x equals y, right? Back from way back here, x and y are equal. So y also equals 1 over the square root of 2. And therefore the coordinates of my point here are, coordinates of this point are 1 over the square root of 2, comma 1 over the square root of 2. So for the 45-degree angle, this is the angle I'm interested in right here. This is the angle T equals, I'll do it this way, T equals 45 degrees. We have these coordinates. I'm going to make a note of those over on the right-hand side of the screen, and we're going to leave that there during the rest of this video. And we're going to have a lot more values to add to this chart, so I want to have a kind of a permanent record. Now, one thing I want to mention here before we go on is that T can be measured in degrees or it can be measured in radians, and so it's worth knowing how big 45 degrees is in terms of radians. So let's do a conversion. This is good practice. 45 degrees times, and I'm going to multiply this either by pi over 180 or by 180 over pi. Remember that the 180 is in degrees, so I'm going to do the 180 on the bottom because I want the degrees to cancel. So I have my 180 degrees down here, and I have pi here. And then from there I can cancel my degree symbols, right? It's kind of like doing chemistry. And that gives me 45 times pi over 180, but then this can be reduced. 9 goes into both 45 and 18. If 9 goes into 18, it's going to go into 180. So 45, 9 goes into 45 5 times. 9 goes into 18 2 times, so it's going to give me 20. And then 5 goes into 20, so that's going to give me pi over 4. So another way to write 45 degrees is as pi over 4. All right, so now we have it in both degrees and radians. This is the same angle. They have different names because here we're measuring in degrees. Degrees are very, very small. Here we're measuring in radians. Radians are much bigger, right? 1 radian is just a little bit smaller than a sixth of the circle, whereas 1 degree is 1/360th of a circle. Now your textbook goes on to say, oh, what happens if we rationalize the denominator? I'm going to erase some of this conversion scratch work that I just did here. I'm going to erase this part of the screen because I need a little more room to demonstrate something else. Go ahead and erase that. And now I want to say 1 over the square root of 2 times, we're rationalizing the denominator here. Hope you remember this from algebra. It's the square root of 2 over the square root of 2 times the square root of 2 is the square root of 2 squared, which is just 2. So another way to write 1 over the square root of 2 would be the square root of 2 over 2. And that's fine. You're welcome to write it that way, but I don't really care, right? If you would rather just leave it like this, that's fine. Again, these are equivalent, so pick the one you like the best and stick with it. I'm going to go ahead, at least for now, stick with 1 over the square root of 2. Okay, so that's how we find the cosine of 45 degrees, or the cosine of pi over 4, and the sine of pi over 4. But what about 30 degrees and 60 degrees? These are what we call well, there's a lot of different names for these, but 30, 45, 60, and 90 degrees are all going to be important angles. In fact, so is 0. So I'm going to make a little bit of room in the table for 0 degrees, 0 radians. Oops. Just move everything down a little bit. I think I moved it down too far, but that's okay. Move 30 down. Let's stick 0 in there. Okay. Remember that 0 degrees is equal to 0 radians. I can put both of those in there. I feel like I should have made this column a little bit wider. All right, but now we have room to talk about these other special angles. So starting from scratch, I've made myself a slightly bigger circle this time. We're going to stick with a radius of 1 here. So the radius of this circle is 1. And what I've tried to do here is draw a 30-degree angle here and a 30-degree angle here. It's not very accurate, but pretend with me, because this is it's the idea that's important more than the accuracy of my drawing. Now, again, from geometry, hopefully you remember that if all 3 sides of an angle have the same measurement, then all 3 angles have the same measurement. In other words, the length of the side of a triangle affects the size of the angle. And if all the sides are the same, then all the angles must also be the same. So if that's the case, then we have 3 angles of the same sides. Let's call that x, has to equal 180 degrees. Divide both sides by 3, you get x equals 60 degrees. So all 3 of these angles have to be 60 degrees. That one's 60, that one's 60. And that means also that this third one here, this third big angle, is 60. And it's also evident that this is 60 because I drew this by putting a 30-degree angle here and a 30-degree angle here. So this is also 60. But that means this one's 30 and this one's 30. So let's go ahead and label that as well. Notice that I've left the degree symbol off on these primarily because of the amount of space I have to work with, or the lack thereof. Now also remembering that this line right here has a length that we defined as y, right? It has the same length as is the height of the y coordinate, or the height of the coordinate there. Right? So if this is x comma y, then this point has a y coordinate of y, which tells me that that's the distance I have to go in that direction. So that has a length of y. Well, if that's the case, then this line also has a length of y. The right pen here. This line also has a length of y. So this whole thing right here is 2 times y. But this is an isosceles triangle. So all 3 sides have the same length, which means that this side also has a length of 2y. And so that tells us that 1, the length of that radius side, is equal to 2y, the length of this other side. So the length of this side of this triangle and the length of this side of this triangle are equal. They're the same. Dividing both sides by 2, I get y equals 1/2. But we have another way to describe y. We called y sine of theta, or sine of t in this case. So sine of t equals 1/2. What is t? T is 30. So sine of 30 degrees equals 1/2. So the sine here, so over on my chart, the y is 1/2. Now that is the length of the side that goes from the x-axis out to the coordinate point that we're interested in, right? So we're looking at t equals 30 degrees. We're looking at this triangle here. So we have y coordinate of 1/2. So what is the x coordinate? Well, we have a right triangle now. So I can say that x squared plus y squared equals r squared. Well, that's 1. 1 squared is 1. We don't know x. That's what we're trying to find out. But we do know y. It's 1/2. That still has to equal 1. So x squared plus 1/4, I just squared this to get 1/4, equals 1. And if I subtract, I'm running out of room here, if If I subtract 1/4 from both sides, I get x squared equals 4/4 minus 1/4 is 3/4. And if I take the square root of both sides, I get x equals the square root of 3 over the square root of 4, which is 2. So for 30 degrees, the x value, the cosine value, is the square root of 3 over 2. What I just found here is the x value. When I know y, I found the x value. So I found the length of this side here. I know y. I just found that that was a half. But now I also know x. All right, I think we're going to do 60 degrees in class because this video has gotten way too long. Let me erase just a little bit. Okay, I ended up erasing everything. I want to take a look at what are the cosine and sine of 0 and the cosine and sine of 90. Well, if this is my initial ray and I don't go anywhere, in other words, I start there, but I don't move in either direction, then that's 0 degrees. I've traveled 0 degrees or 0 radians, right? So now I'm looking at this row in my table, and what are the x and y coordinates there? Well, this is a unit circle. So if I remind us that this has a radius of 1, then any radius is going to be 1. Okay, so what are the coordinates of this point? They are 1, 0. And therefore, my x and y coordinates are 1, 0. Just like that. Equally, at 90 degrees, I have the coordinates 0, 1. So for 90 degrees, I have cosine equals 0 and sine equals 1. I could, in fact, put commas between all of these because these are coordinate pairs. They're points, right? I've been listing them as values, but they're points. We're going to come back and do this one in class, I think. That's my current plan. And I'm also going to have you come back during class, and maybe you want to work on this a little bit before class if you feel like it, but we'll work on them in class. And remember or figure out what the radian measurements are for these other angles. All right, this video is much longer than I wanted it to be, so I'm going to stop there, but I will point out that I'm not going to make a video for the subsection called Finding the Domain and Range of Sine and Cosine, because that subsection is very, very short, and we'll just discuss it in class. So our next subsection is going to be about reference angles.